the lesson about increasing and decreasing functions with a question. And that question is, what can the derivative of a function tell us about the function? And you actually already know the answer to this because we've been dealing with it for some time. A function is increasing when its graph moves up as x goes from left to right, like so. And a function is decreasing when its graph moves down as x moves left to right, like so. And we already know that when a function is increasing, every tangent line will have a positive slope, like so. And when a function is decreasing, every tangent line will have a negative slope, like so. And we also know that the derivative tells us the slope of a tangent line. That means that we can use the derivative to determine intervals for a generic function where that function is increasing and decreasing. This is very important. It's a very important technique, and that is the main goal of this lesson is to become familiar with this idea and be able to implement it. This idea leads to something that's going to give us a test for intervals of increase and decrease for a function. And here it is. If you have a function that's differentiable on some interval, say a to b, if the derivative is greater than 0, being greater than 0 means that it's positive. If the derivative is positive, then the function is increasing on the interval from a to b. If the derivative is negative, less than 0 means negative, then the function is decreasing on that interval. It's got to be true for every value of x in the interval of interest. And of course, we've talked about this before as well. If the derivative is exactly 0, then that function is constant on the interval. It's leveled off. It's not increasing or decreasing. This is the basis of the important things that we want to learn and practice in this lesson. I can sort of summarize what I've said so far in this statement. For a continuous function f prime of x can change signs only at x values for which f prime, the derivative, is equal to 0, or at values for which f prime is undefined. And we've talked about these types of values before. The derivative is 0 or the derivative being undefined. An example of a place where a function is undefined is if you get a sharp point, a cusp. We've talked about this in the past. So the graph on the left shows a typical place where a function might have a derivative of 0. It's where it levels off. And the function on the right, the graph on the right, shows a cusp where you would get an undefined derivative. And we've talked about these things before. We're now giving this a name. The x values for those two types of situations where the derivative is either 0 or where the derivative is undefined, those x values are called critical numbers of the function. And we'll be using that terminology a lot, so get used to it. Critical numbers are values of x where the derivative is 0 or where the derivative is undefined. Very important concept. And just to be clear, I want to put a formal definition up of a critical number. If f is defined at a value c, then that value c is a critical number of f when the derivative is 0 at c or when the derivative is undefined at c. It's just a formalization of what I had just said. And we're going to be taking various functions and finding intervals where the function is increasing or decreasing. So I want to lay out a set of guidelines that's going to help you do that in an effective and efficient way. So here are those guidelines, and you need to practice them because you're going to be using them a lot. First thing you want to do when you're looking for intervals where a function is increasing, decreasing, is to find the derivative, always. Once you find the derivative, then you want to find the critical numbers, and that involves, as the definition I presented earlier says finding values where the derivative is 0, and if there are any, values where the derivative is undefined. Once you find your critical numbers, you'll notice that the critical numbers divide the number line into distinct intervals. So if you think about putting those critical numbers, labeling them on a number line from left to right, you will see that you've divided the number line up into distinct intervals. And what you want to do is choose a test value in each interval, and for each of those intervals, each of those test values, you want to find the sign, whether it's positive or negative, of the derivative, the sign of the derivative. Because when the sign is positive, you know the function is increasing on that interval. If the sign is negative, you know the function is decreasing on that interval. And finally, you want to interpret your results. And to reiterate, a positive derivative in that previous step means the function is increasing on that interval, while a negative derivative, again from step 3, means that the function is decreasing on that interval. So you're going to take the derivative, use the derivative to find the critical numbers, use the critical numbers to divide the number line into distinct intervals, then take test values in each interval and determine whether the derivative comes out positive or negative for those test values, and those test values determine whether the function is increasing or decreasing on those intervals. Positive derivative, increasing. Negative derivative, decreasing. You've got to learn this procedure. Go ahead and do it. Practice it a lot. Our first opportunity to practice is in this example. Suppose I ask you to find the critical numbers of the function f of x is equal to 1/3 x cubed minus 4x. The first step is to find the derivative. That's simple. This is a polynomial function. Bring the 3 down, multiply by the 1/3, that gives you 1. Drop the 3 to a 2, and the derivative of negative 4x is just negative 4. So f prime of x is x squared minus 4. Second step, find all critical numbers by finding all x for which the derivative is 0 and the derivative is undefined. One thing that you can just go ahead and bank on, and we've talked about how nice polynomial functions are. Polynomial functions are defined for all real numbers, and the derivative of a polynomial is still a polynomial. So there will never be undefined values for the derivative of a polynomial function. So anytime you're asked about critical numbers for a polynomial function, you really don't have to worry about any undefined derivative values. You only have to worry about the places where the derivative is 0. That's true for all polynomial functions, not for all functions, but for all polynomial functions. Sometimes we will have to deal with the derivative being undefined, and we'll get to an example of that shortly. In any case, we want to set the derivative equal to 0. Well, we found out the derivative was x squared minus 4. If you add 4 to both sides, you get x squared equal to 4. There are 2 values of x that satisfy that condition, and that would be plus or minus 2. So those are your critical numbers. What if I continue this problem by asking a further question? What if I said, now let's find the intervals on which the function is increasing and decreasing? That means I've got to move to step 3 under my guideline. Step 3 says to take those critical numbers, they divide the number line into distinct intervals. Put them on a number line, label them in order from left to right, and then choose a test value in each interval. So there are only 2 critical numbers, minus 2 and 2. I place them on a number line. I take a test value in each interval. So you can pick anything to the left of minus 2. I chose minus 3. Pick something between minus 2 and 2. You can choose anything that's in there. I chose 0. Choose a value bigger than 2. Again, you can use anything bigger than 2. I chose 3. And you take those test values and you plug them one by one into the derivative, not the original function, but into the derivative. So if you plug minus 3 into the derivative, which is x squared minus 4, you get minus 3 squared plus 4, which is 9 minus 4, which is 5. You really don't care what the value is other than the fact that it's positive. So label your interval as positive. Then you move to the second test value, 0. Plug 0 into the derivative. 0 squared minus 4 is negative 4. That's negative. Again, I don't care about the magnitude. I just care whether it's positive or negative. And lastly, take 3, plug it into the derivative, and you get 5, which is, again, positive. And that's what I call an increasing-decreasing chart. To me, that's the best visual representation of this process that lets you easily analyze what you've got. So the last step, step 4, is to interpret what you've got, remembering that the derivative being greater than 0, which means positive, the function is increasing. The derivative being less than 0, which means it's negative, implies that the function is decreasing. So all the plus signs are indications of intervals where the function is increasing. The negative sign, in this case there is just one, is where the function is decreasing. So it's increasing on the interval from minus infinity until it gets to minus 2, and then it's increasing again on the other end from 2 to infinity. And then it's decreasing in the middle, that interval from minus 2 to 2. This is not difficult, but you do have to practice. The more you practice, the better you're going to get at it, the less likely you are to have to go back and rely on looking back on what the steps are. Your goal is to practice and wean yourself away from the guidelines written out and just have it in your mind so that as you go through the process, you can do it on your own. Do another one. Here we want to find the intervals on which the function x squared minus 4 to the 2/3 power is increasing or decreasing. Now this is not a polynomial function, so we may have a little more work to do here. Let's just see. The first step, though, is still to find the derivative. The derivative is going to be by the chain rule, or in this case, what I sometimes call the general power rule. You bring the 2/3 out front, you write the base down, you subtract 1 from 2/3. 2/3 minus 1 is 2/3 minus 3/3, and 2/3 minus 3/3 is negative 1/3. And then you go back by the chain rule or the general power rule and multiply by the derivative of the base. The base is x squared minus 4. The derivative of that would be 2x. So you take the derivative and then simplify it. Remember, the 2x is like 2x over 1. So if you're really talking about simplifying this and probably getting rid of that negative exponent, you might want to think of that as 2x over 1 and that being over 1. So when you're simplifying this, the 2 times the 2 is going to give you a 4, and the 4 and the x are in the numerator. The 3 is in the denominator, and when you drop the negative 1/3 and push that exponential expression down to the denominator, it'll become a positive 1/3. So when all is said and done, the 2 times 2 is 4, it stays up, the x is up, the 3 is down, and the negative exponent up top tells you that you can push it down and make it a positive 1/3. Second step, find the critical numbers. Well, the critical numbers come from setting the derivative equal to 0 and looking at where the function is undefined. For a polynomial function, we didn't have to worry about the derivative being undefined, but this is not a polynomial function, so you really have to be careful here. You can easily see that you can make that derivative 0 by making x 0. And I've said this several times, but it's really a good way to think of it. When you're trying to make a fraction equal to 0, all you have to do is look at the numerator, because the denominator cannot be set equal to 0. That gives you an undefined expression. In fact, that's where you're going to find the values where the derivative is undefined. But for setting the derivative equal to 0, you really only have to look at the numerator when you have a fraction. So x equals 0 is obviously going to make that derivative 0. But this is not a polynomial, so I also have to look at the denominator and see if there are any values that make the function undefined. And if you think about this a minute, you'll see that x squared minus 4 down in the denominator is going to give you a problem if you let x either be plus or minus 2, because 2 squared is 4 and negative 2 squared is 4, and 4 minus 4 is 0. So you're going to be dividing by 0, and those are values that make the function undefined. And remember, look back up at step number 2. You're looking for values that make the derivative 0 and the values that make the derivative undefined. So when you have a fraction, the numerator gives you the values where the derivative is 0, and the denominator gives you the values where the derivative is undefined. So when all is said and done, you've got three critical numbers, plus or minus 2 and 0, and you want to put them in order from left to right. So it's minus 2, 0, and 2. Those are your critical numbers. That tells you that if you put minus 2, 0, and 2 on a number line from left to right, that breaks the number line into intervals to the left of minus 2, that's minus infinity to minus 2, between minus 2 and 0, between 0 and 2, and then to the right of 2, which is 2 to infinity. So once you've got the critical numbers, you visually put them on the number line, and that breaks the number line into the intervals that you have to check. And remember how you check them. You take a test value in each interval. So you take something to the right of to the left of minus 2, I took minus 3. Something between minus 2 and 0, I took minus 1. Something between 0 and 2, I chose 1. And something bigger than 2, I chose 3. And then you take those test values and you plug them back into the derivative. Now notice, I went ahead and rewrote the derivative as a cube root because I'm going to plug in numbers. WebAssign is not too particular about how you leave your answers, but if you are going to have to plug in numerical values eventually, it's better to go ahead and write these things as radicals instead of fractional exponents. How do I do this? I take minus 3, that's my first test value, and plug it back into the function. Up top, you'll end up with negative 12, and down bottom, you'll end up with 3 times the cube root of 5. Again, I don't really care about the magnitude. I just realize that that's a negative number over a positive number, which makes me have a negative result. So in the interval from minus infinity to minus 2, with the test value of minus 3, I come up with negative. That tells me that the function is decreasing in that interval. Then I take the interval between minus 2 and 0 and test the test value I chose, which is minus 1, and plug it into the derivative. Remember, you're plugging into the derivative. That gives me a minus 4 up top, and you get the 3 times the cube root of negative 3. Now, just be careful here. You can't take the square root of a negative number, but you can take cube roots, any odd root of a negative number, and it just comes out negative. If you ever get confused, just think about the example of the cube root of negative 8 being negative 2, because negative 2 times negative 2 times another negative 2 is negative 8. So you can have a cube root of a negative number, you just can't have the square root of a negative number. And the cube root of a negative number comes out to be negative. So what you end up with is a negative number on top and bottom. If you divide a negative by a negative, you get positive. So the interval between minus 2 to 0 has a positive derivative. Keep going. Now you take the interval between 0 and 2, whose representative test value is 1, plug that in, and you end up with a positive over a negative. That's negative. And finally, you go to the last interval, test value of 3, plug a 3 in, and you end up with a positive over a positive, which is positive. And that increasing decreasing chart tells you everything you need to know about where the function's increasing or decreasing. And again, negative means decreasing, positive means increasing when it comes to the derivative. So what you know is you've got decreasing, increasing, decreasing, increasing, and if you want to formally write that out, it's decreasing on the intervals from minus infinity to minus 2 and 0 to 2, and it's increasing on the intervals minus 2 to 0 and 2 to infinity. I just want to point out that the textbook and the electronic textbook and the software doesn't use this increasing decreasing chart like I do. They use this table. So I just want to have shown every column in that table represents one of the intervals on my increasing decreasing chart. So if you see it somewhere, you can do it that way, but I think you get a better visual, a better mental image of what's going on if you do it my way with these test intervals on a number line than by putting the same thing into a table. But in case you ever see it, that's all they're doing. They're taking a table method instead of doing it visually on a number line, which I think is more useful. Either way you look at it, you get the same result, that the function is increasing on two intervals and decreasing on two intervals, as I indicated earlier. Let's do another one. Find the critical numbers of the function x over the quantity x squared plus 9. Well, that's a quotient, so you're going to have to use the quotient rule. The quotient rule says you take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. When you simplify it, you're going to get 9 minus x squared over the quantity x squared plus 9 squared. What's the second step? Well, what they asked for, the critical numbers. The critical numbers come from saying the derivative equal to 0 or having the derivative undefined. As we discussed in the last example, when you have a fraction, the only way you can make a derivative 0 is for the numerator to be 0. And it's easy to see that if you square either 3 or minus 3, you get 9, and 9 minus 9 is 0. So you get critical numbers from setting the derivative equal to 0 whenever x is 3 or minus 3. But the denominator is a little different. You're never going to get a 0 down there. Think about it a minute. Everything's plus in squares. If you take any number, whatever you make up, and square it, it's not going to be negative. So x squared is either going to be positive, or if x is 0, it's going to be 0. But then you turn right around and add 9 to it. So that's going to be a positive number, and then you square it, and it's still going to be positive. So there is no way the denominator can ever be equal to 0. That means there aren't any values where the derivative is undefined. So the only critical numbers are plus and minus 3. Here's another one. Find the intervals of increase and decreasing of the function f of x is equal to the square root of the quantity 9 minus x squared. Of course, you want to write that as a 1/2 power because the first step is to take the derivative. Take the derivative, bring the 1/2 down, write the 9 minus x squared, which is the base, down. Subtract 1 from 1/2, you get a minus 1/2. And then by the chain rule, you take the derivative of the inside. Of course, the derivative of 9 is 0, and the derivative of minus x squared is minus 2x. And notice those 2's will divide out, and so you end up with minus x times the quantity 9 minus x squared to the minus 1/2. Again, you know from experience you're going to have to plug numbers into this later, so you might as well get rid of that negative 1/2 exponent. So if you think of the negative 1/2 as being in the numerator, if you push it down, it becomes a positive 1/2 in the denominator, and a positive 1/2 is the square root. You should be good at this now because we've done it for quite some time now. In any case, that's your derivative. Now I want to find the critical numbers. Well, the critical numbers come from where the derivative is 0 or where the derivative is undefined. This is another fraction, and as we've said over and over again now, the only way to make a fraction 0 is for the numerator to be 0. Well, with that x sitting there, it's obvious the derivative will be 0 if x is 0. What about the denominator? Well, you're squaring x and then you're subtracting it from 9. So if x were either 3 or minus 3, when you squared it and said 9 minus 9, you're going to get a 0 in the denominator. So this time you get a critical value from the numerator of x equals 0. You get two critical values from the denominator plus or minus 3. Continuing, I put the critical values on a number line from left to right, and I do a test value in each interval. So I chose minus 4 to the left of minus 3. I chose minus 1 between minus 3 and 0. I chose 1 between 0 and 3, and I chose 4 bigger than 3. And I'm going to make short shrift of this. When you try to plug these things in, look what happens when you try to plug a negative 4 in your test value. Well, you square negative 4, you get 16. Well, 9 minus 16 is negative, and you've got it under a square root. You can't take the square root of a negative number. That should clue you in on the fact that numbers to the left of minus 3 aren't even in the domain of the function. You get an undefined value when you try to plug that test value in, and it sort of makes you say, aha, see, I can't plug numbers bigger than minus 3 into the function and get a value. So just forget about things to the left of minus 3. They're not even in the domain of the function. Can't do them, just forget about them. Then you move between minus 3 and 0 with your test value of minus 1. If you plug minus 1 in there, I didn't show the work because it was just clutter up the screen, but if you plug it in, you're going to get a positive value. And then you take a number between 0 and 3. I used 1 again because it would clutter it up. I didn't show the work, but you get a negative value. And finally, you pick a number bigger than 3, and I chose 4. And again, you end up with 9 minus 16 in the bottom, which is going to be a negative number. You cannot take the square root of a negative number. That means the function is undefined, and you say, oh yes, I remember now. That's not going to be in the domain of the function, because when you square anything bigger than 3, it's going to be bigger than 9, and you're going to get a negative in the denominator. So there's just nothing over there to the right of 3. So the domain is restricted to numbers between minus 3 and 3. But within those intervals, I can now say, interpreting my increasing decreasing chart, that the function is decreasing where there's a minus sign, that would be 0 to 3, and increasing where there's a plus sign, that's minus 3 to 0. Once you get the hang of this, it's not that bad, but it does take practice, and you have to think about what you're doing on every step. Polynomials are the easiest of all to work with. If you're working with a function that's a fraction, you've got to deal with it very carefully. Or sometimes you're dealing with something that becomes a fraction when you take the derivative, and you have to be careful. It's not difficult, you just have to be careful. You have to practice every variation so that you've been through it before, and the more you practice, the more it's going to flow.